calculation just for that. Any questions about the quiz and labs? They're good. I saw a little problem with the superposition with the 3 power supplies. And if you are not getting 100 point on that, please review the videos and do a calculation. If you still couldn't get it, welcome to visit during office hours.
On this quiz or
the previous one, the 3 power supply. And this one, I think I already did it multiple times in the class, right? So if you look at the notes in the video, I should have solution over there. So, I mean, after you got all the numbers for it, there's a very easy way to verify it, because if you have a 3 power supplies, 1, 2, 3, feeding into that deck. So immediately you know that if the V out is over here, right? If V out is over here, you know that this is LSB, this is MSB, right? And the 1 over here, if you have a 1, 0, 0, it is basically 1, 0, 0. So this one is going to be half of the VREF. If 10 volts for the full range, or let's say use 5 volts. If these are all 5 volts power supplies, this one represents 2.5 volts. And this one is LSB, which is 5 over 8, right? Which is 0.625 volts. So without you going through all these superposition and Thevenin's equivalent circuit, you can immediately find out the answer, which is 3.125 volts, without calculating anything. Okay? But the problem does require you to show all the process to get the credit. But after you do all the calculations, you can verify the answer really quick by doing this. Right? Shouldn't lose points anymore in the future. Okay, if I put on a midterm exam or somewhere else. All right, now let's talk about the star logic. If we summarize everything in the table, the first column we name it as cycle number, and this is the digital 3, D2, D1, D0, and this is a comparator's output. First question, what's the resolution of this ADC? For what? 4-bit, right? It's a 4-bit. So cycle 1, cycle 2, cycle 3, cycle 4, cycle 5. For 4-bit ADC or star ADC, we need 5 cycles to finish the conversion. We did it on Friday last week, showing all these intermediate numbers during the conversion, but now it's trying to reinforce it. So for cycle 1, what's the initial number for all the Ds? We can use circuits to reset it to that way, right? Just 1 zeros. We can reset the first one to make it 1 all zeros. But we start with one number. Remember, what is that number? Yeah, we start with this number. Okay, so at the very beginning of the conversion, we reset all these bits and set this bit to make it 1 zeros. That's doable. We can use a circuit to do that. Okay, this is the very beginning, the first state of the star ADC. And the comparator's output, for example, is A3 afterwards, after the comparison, because the DAC is going to convert this number into an analog voltage, and it's going to being fed back to the comparator's input. and eventually it's going to output a voltage here immediately. There's no control logic in the middle. It's directly the speed of light. The electrons are moving around and eventually give you that A3 as a comparator's output. So in the next cycle, how the numbers are moving and where you want to plug this A3 in to all the D's. What's going to happen to these numbers? What's happening? Yeah, but here, what is about? What is just A3, right? That's a comparator that can be 1, can be 0, but we just plug it in into here. And then because the structure of the ADC, this one will be converted into this analog voltage, this analog counterpart, and being fed into the input of the comparator, and then it's going to generate another comparator output, right? And this goes where? Yeah, below, just behind A3, right? Following A3 and shifting the 1 to the right for one more time. And this one is the number of the input of the DAC. So the DAC again will generate the analog voltage and be fed into the comparator's input, which will generate another comparator output, which is A1. And then we keep plugging in A1 right after A2. Okay. Same process is going to generate A3 as a comparator's output. And the next cycle is going to plug in A0 as the LSB bit. Okay. So you can find out eventually the converted or the final result of the ADC or DAC. Let's say ADC is all the comparator's output, right? It's exactly all the comparator's output, but you put A3 at the MSB bit, A0 at the LSB bit. Okay, let's take a look at another example, then we will look at the circuit to implement this logic. This is what we want, right? So as a customer, we request a circuit to implement this logic. This is what we want. Then we just design the circuit to implement this logic. That's how it works. So for example, Vref is 10 volts, and at the moment, Vin is 4.25 volts. So let's show all the conversion, all the intermediate numbers, or the entire conversion process of the SRDC. You still remember the structure of it? VDC is here's Vin. So what is in front of it? What is before Vin in the SRDC structure? Sample and hold, so it holds it. That's why you are getting a static voltage. It's holding it there. It's a DC voltage, which is 4.5 volts. It's holding there. And this is VDC. So this comes from where? No, that's the DAC's output, right? And you got a SAR here. And the SAR feed the digital input to the DAC, and which generates the analog voltage and being fed into the inverting terminal of the comparator. Remember, it's in the inverting, so the VDC is connected to the inverting terminal, not the non-inverting terminal, and the VIN is connected to the non-inverting terminal, not the inverting terminal, which is important because this determines the output of the comparator. You want to plug into the numbers, okay? So for example, V in right now is 4.5 volts. It's being held there. It's not changing because of the sample and hold circuit. Okay, so the voltage comes in and the cycle starts. So the star is going to output a number first. What is that number? This. It's a 4-bit ADC, so it's going to output a 1000 as a very initial state, which is how much, what's the voltage? It's going to be 5 volts, right? Okay, so 5 volts compared to, you got 5 volts here, compared to 4.5 volts, is outputting a 1 or 0. Zero, right? Because the inverting is larger than the non-inverting, so saturating the output of the comparator at 0 volts, and we're plugging the 0 volts to where? To the MSB, right? Okay, what's next? What is this voltage? 2.5. So 2.5 is here or here? Where is 2.5? Top, bottom? Bottom, right? So this becomes 2.5 at the next cycle. And compared to 4.5, you're getting a 1. And now it becomes 0, 1. 1, 0. Keep shifting these guys to the right and plugging a 1 here. So what's the voltage of this guy? Is that 2.5 plus 1.25? So it's 3.75. Compared to, so we got 3.75 volts. Compared to 4.5, it's going to output a 1, right? So it's going to plug in 0, 1, 1, 1. Oh, this is a black one here. Is that correct? So what is this? How to calculate it? Because this is 1 LSB less than 5 volts, right? Because this is 1000 minus 1 LSB becomes 0111, right? Which is 5 volts minus 0.625 volts, which is 4.375 volts. So this is 4.375 volts. And compared to 4.5, you're getting a 1 or 0. 1 again, right? Okay. So eventually it becomes 0111. Should be all right. As a final result. Any questions on this? You don't have questions on this? Let's have a quiz on this now. How is it? Friday? Okay. So how do we implement it? How do we make it happen with the circuit? So this one is a comparator's output, which is here, right? We label it as COMP. That's a comparator's output, which is exactly, it's just same wire, same trace. It's just directly connected here. Because what we're drawing here is part of the SAR logic, the SAR block here. So that comparator's output is being fed into this box, so which is this one, fed into the box here. It's just part of it. I'm showing half of it at the bottom half right now. And assuming that there's a circuit on the top, is able to shift the ones over here to set it. So at the very beginning, you have 1 and all zeros. So these are D flip-flops. So the input here is our D's, data, and these are Q's. Remember what the D flip-flop does? So for this one, at the rising, since I didn't draw a bubble here, if you see a bubble, it's 0 active, which means that falling edge is going to trigger it. But I didn't draw the bubble, which means it's 1 active. So if there's a rising edge, it's going to trigger the D flip-flop. It's going to send the data, whatever at the data line, D to Q. It's like a latch, right? Whenever you trigger it, it sends the data from the left to the right. Very simple. It's a rising edge triggered, which means whenever it's stabilized at 1, no matter how D changes, the change will not be sent to Q. It only happens when the rising edge arrives at the clock. So these are clocks. It's going to send D to Q. Okay. So at the very beginning, this one is being set, which means, so set is gonna, which means you force it to be 1, force the output to be 1. If you do a reset in digital, you force it to be 0. So that's the language in digital, the digital world, right? Okay. So assuming that there's a circuit on the top, I didn't draw it, but there's something on the top, is able to give you that 1 and zeros and shift it. It's called sequencer, but we are going to talk about sequencer later. And now this is a data register, I believe that's the name, or code register. So the name of it is called code register. Okay. So something on the top is able to send a 1 here and 0 for the rest of them. So according to this conclusion, so set is going to give a 1 to Q, right? Because I'm setting it. No matter how D changes, doesn't matter because it's going to force the Q, the output, to be 1. It's going to override everything from D. So if I set it, Q will be forever 1. Unless I put a 0 here, it's going to release it. So it behaves like a D flip-flop. Otherwise, if I put a 1, I set it, you got a 0, you got a 1 at the output. And there might be a reset pin as well, right? You can have a reset pin as well. Whenever you give a 1 here, it's going to reset your Q, which will output a 0, right? But we are not using that reset right now, just using a set. So set is going to set it to 1 no matter how D changes. Remember that. So 0 sent to set is not going to change anything. So if you put a 0 to set, you didn't turn on the set function, you release that D flip-flop, so it's going to behave like a D flip-flop. Okay? All right. So at the very beginning, I didn't send anything to it. So it's outputting 1, all zeros, 1, 0, 0, 0. So the last one is not outputting any data, it's being used as a clock for the previous one. So don't have to worry about this one for now. So for a 4-bit SAR ADC, you need 5 D flip-flops in the SAR code register. Okay, so whenever the sequencer on the top, there's a circuit on the top, I'm going to show that later. Assuming that there's something on the top, it's going to shift this one to the right by 1 bit, but not changing the zeros, okay? So if this one is being shifted to the right, and now it becomes 0, 1, 0, 0, 0, what's going to happen? What's going to happen? So at one moment, right? So the circuit on the top, the mystery circuit on the top, is able to shift that 5-bit digital data to the right by 1 bit, right? So 1 will be here, and then it's being replaced by a 0 because it's just simply shifting. What's going to happen? So this one won't be set anymore, and instead it's being released because I'm putting a 0 on the set, so I'm not turning on the set function. So this one becomes a D flip-flop. It's going to work, right? So this is going to be a functioning D flip-flop. Okay, but however, I'm setting the second one. So the second one is going to output a 1 here. So output a 1 here. Remember the last state, I got a 1, 0, 0. So it was a 0, but now it's a 1. In the next cycle, this becomes a 1. And I'm shorting this one. I'm shorting this Q. If you look at the hardware, this one is being shorted to the clock of the previous one. What's going to happen? So at a moment, right, Q was 0, and after the first cycle, at the beginning of the next cycle, it becomes 1. So there will be a rising edge for Q. Does that make sense? So from Q changes from 0 to 1, so there will be a rising edge. And Q is being shorted to the clock of the previous one, of the first one, okay? So it's going to give a rising edge to the clock of the previous one. What's going to happen? It's going to send a D to Q because it's a functioning D flip-flop. Why? Because it's being released. And why it's being triggered? Because I got a rising edge. So D flip-flop is having a rising edge. It's going to send D to Q. So what is D? The comparator's output. So what is that first cycle's comparator's output in this table? A3. And it goes where? It goes where in the circuit? Let me know. It goes where? So A3 goes where? A3 is right now at this line, right? It's the same line. See, the comparator's output is being shorted to all the D's. Okay, so now I have A3 right now is floating at on that wire, right? Remember, I have a rising edge here. I have a functioning D flip-flop. So A3 is being shorted to D. So after that rising edge, A3 will be sent to where? Q. So this becomes what? Does that work? Okay, so I'm plugging that A3 to MSB, and it works. One question, why A3? Because the comparator's output is being shorted to all the D's of all the D flip-flops. So why only this Q is getting A3 but not the other ones? They don't have the rising edge. Are they active D flip-flops? Yes, they are. They are not being set, except this one. But these ones are not being set. So they are fine. They are functioning D flip-flops. However, they don't have a rising edge. Why they don't have the rising edge? Because there's only one logic 1 here being shifted. Okay, when you shift it, there's only one rising edge happening in the entire circuit that's being sent to the previous one, to the previous D flip-flop. So after that cycle, you got an A3 here. And according to the table, the next one should be a 1. Are we getting a 1 for the next one? And why? Are we getting a 1 here? Yes, it's the same Q. The Q becomes 1 because the rising edge, remember? It's the same Q. I'm shorting that. I'm directly dragging that. It's the same wire. What about the other ones? It was 0. There's nothing to make it a 1, so there are still zeros. So after the first cycle, you got A3100, A3100. It works really well. What about the next cycle? The next. So we want to make sure A3 will be kept there, right? It's not being stored. It's not being shifted or being changed. So what's the next cycle? You are getting 0, 0, 1, 0, 0, right? Okay. The comparator's output from here is still being shorted to all the D's. It's not being changed. It's still shorting to everywhere. It's feeding the data to all the D's, but only one is going to work because you got a 1 for the third D flip-flop. What's going to happen? There was a rising edge at Q, right? And then it becomes 1 because this guy is being set. So it's trying to jump from 0 to 1. And that one is the same wire will be fed into the clock of the second one. Okay, what's going to happen? You got A2 here right now. So A2 is sitting here at the D. So the rising edge is going to send A2 to Q. Okay, so this is what we want, right? However, now let's take a look at A3. Is A3 being changed? Why? But I mean, for the circuit, is A3 being flipped? And why? That's right. It's just a 1, right? You had a 1 here. It's not changing. You need an edge to trigger it, but it's not an edge. Okay? So A2 will be here. A3 is safe. Are we getting a 1 here? Because on the table we need a 1, right? Are we getting a 1 here? Yes, we are, because it's being set. So this one is still 0. So we can keep doing this, and eventually we can find out we're getting A3, A2, A1, A0. So now let's answer this question. Why do we need the number 5 D flip-flop at the end? We're only using 4 of them to holding the data. Why do we need a last one? And we are not using this Q at all. We see other ones, the Q, you got 2 branches. One is the output, another one is got another wire for the clock to trigger it. But this Q is different. This Q only behaves as a clock for the previous one, but now outputting this Q. I already said the answer because this Q is only being used as a clock. Because you always need someone behind you to trigger it, right? The fourth one you need to get triggered. So you need one more behind it to trigger it, to provide a clock for it. Right? Because the second one provide a clock for the first one, the third one provide a clock for the second one, the fourth one provide a clock for the third one. I mean the fifth one provide a clock for the fourth one, right?
So it needs the clock to trigger because there's no rising edge.
Because this one, so remember this little one here will be keep being shifted to the right, and eventually it will be shifted here. And then this one will be set. There will be a rising edge, and this is going to trigger it, so it's going to register the A0 to here. Mm-hmm. Make sense? We're going to build this in LT-SPICE. It works. It's going to work. So now let's look at the sequencer. The code register is this guy, and the sequencer will be another 5 D flip-flops on the top. So you need a 1, for example, we design a circuit, all the D flip-flops need a 1 to set it or reset it. Right? And there will be a clock wire. And we make a connection this way. You'll be able to tell why in a bit. So we connect the first D flip-flops set pin to all the reset pins of the rest of the D flip-flops. And the Q, again, the Q will be the output. And now we just call it reset. It's just the name of the pin. Doesn't mean it's resetting the first one. It's setting the first one actually. And then we feed all the Q's to the D's, to the next D. Remember, what do we want from the sequencer? Let's don't think about all the complexity here. You just feel free to request it, right? So what do we need? Designing a circuit to implement it, that's something else. It's the next step. But we just, request it. What do we want from the circuit or for the code register? We just need a shifted 1, right? We just need a 1. So that whatever circuit on the top, according to this circuit, whatever on the top should feed a 5-bit digital data to the bottom circuit, starting with 1 0 0 0 0. And every cycle it should shift that 1 to the right and replace that 1 with a 0. That's what we want. Okay? And now we are designing that circuit to do it. So basically you have all these bits, so these wires, right, moving up, these are shorted to these 5 wires of the circuit on the top. So I didn't draw the bottom part of it because the bottom part is the same circuit as this one, the code register. So these are the wires feeding to all the code, all these wires, the 1 and 0s over here. Okay. So now we want to generate a 1 0 0 0 0 at the very beginning, and then shift it to the right. So since I already shorted all the Q's to the D's, it makes sense. It's a shift register. It's shifting the data to the right because every cycle is going to send D to Q, and the Q becomes D. So the a D is the Q from the previous one will send that data to the next Q. So it's a shift register. It's shifting the bits to the right. Okay, that makes sense. That's why we short them together to make a shift register. Okay, but now we know it is shifting. Okay, but we do need 1 0 0 0 0 at the very beginning. So how do we make it happen? Seems like the first one is being set and the rest of them are being reset, right? Which makes sense. I have the wire shorted to set for the first one, but shorted to the reset of all the following ones, which means you want to give a what in order to make it happen at the very beginning of the cycle 1. You want to give what kind of signal to this line to make this happen. You want to give a what to that line to make it happen. Yeah. At the very beginning, just give a 1. Okay, so you need to design the control logic to give a 1 at the very beginning to trigger it or to reset the entire SAR ADC, the SAR logic. Okay, give a 1. So the first one is being set, you got a 1 here, but all the rest of them are being reset. So you need a 1 to reset it. Okay, and next, I need this one to be shifted to the right. And I need a 0 here. How can I make that work? And the next, I need this. I need 2 zeros in the front, right? And then I need this. I need 3 zeros. And eventually I need this. I need one more step actually. Do I need one more step? No, I don't. That's the final step. 5 cycles. 1, 2, 3, 4, 5 for 4-bit ADC. That's all the cycles I need. Okay. In order to do this, anything else do I need to modify to the circuit? I'll let you guys think about it for a second. What should I do? So for the first cycle, no problem, right? First cycle, I just put a 1 here. It's gonna set the first one, reset all the following ones. Okay, the next one, yeah, it's shifting, right? It's shifting. Whenever I trigger the clock is always going, always running, right? Whenever there's the rising edge, it's gonna shift that 1, right? It's gonna shift to that 1 here. Definitely you need to release it, right? You need to release it. Well, after you reset it, you need to put a 0 here to release it. You need all the D flip-flops functioning as a D flip-flop. They need to register D to Q, right? So definitely you need to release it after resetting. Okay? And what else do you need to do to make this happen? Make all this happen? What else? Change the reset location. So you need a person sitting in the chip to move the wire. I think you just say it, right? So what's happening? You describe it. You are plugging a 0 to the front and then replacing the 1s with zeros for all the cycles. So you need a 0. How to put a 0 there? Do you have an input for this guy? So it used to be 1. This guy, right, is here. So it used to be 1. And this one is being registered to the Q. And it's being replaced with a 0. Okay? So you need a 0 here. You need a 0 for the next cycle. You need a 0 for the next cycle, and Q is, after you release it, Q is actually D, right? So then you need a 0 from D. So what should you do? You need a 0 from D. What you want to do? You need a 0 from D. You give a D a 0, right? What does that mean? You give a D a 0. You ground it. Hey, you ground it. But I need a 1 at the very beginning. You have a D to be 0. Always grounded, right? You connect to 0 or to ground is permanently in the circuit. But how can I get a 0 at the very beginning? I get a 1 at the very beginning for Q. Is that going to, if you ground D here, is that going to affect Q at the first cycle to be a 1? No. Why? You set it. Like I said, you force it to be 1. It's not the D flip-flop anymore. Right? Cycle at the very beginning, you set it. So it's being forced to be 1. So you're definitely getting a 1, 0, 0, 0, 0 here at the very beginning. Because this one is going to set it. No matter what you have at D. I talked about that at the very beginning of the class, right? Remember? You set it. So it's not a D flip-flop anymore, even though there's a clock rising edge. It doesn't matter. Because this thing is being set. It's permanently a 1 whenever this is being set. What do you mean D is a default? It means this is a default?
It's connected to ground, or still setting for that first.
No, it's just the ground. Just shorted to ground. Shorted to ground, so it's having a 0 here, but however, it's not sending that 0 to Q because it's being set. Okay? Even though when you release it, it might send D to Q at some point at the rising edge, but it doesn't matter. Whenever I need it to be 1, I set it or reset it. It doesn't matter because I'm connecting this wire to all the reset of the following ones, but set to this one. So if I put a 1 here, it's going to set it. Okay? 0 to what? 0 is going to release it. It's going to be a D flip-flop. So the way that works is at the very beginning, whenever it's ready to do the conversion, right? What's going to happen is the very first step is to reset it, to reset the start logic. Okay, you put a 1 here. No matter what the output here used to be, doesn't matter. Okay, now let's start a new conversion. Okay, then put a 1 here. What's going to happen? This. Okay, it's going to force the output, the Qs of these.
And so, in terms of sampling an analog signal, you send that 1 every new sample?
Every new data point, every new conversion, or every new analog point. Not every cycle of ADC. Every cycle actually. No, you set it every number point being sampled, right? You sample and hold a DC there, right?
Yeah.
And then you reset it at the very beginning, and then put it to 0 for all the following steps of the conversion. And then whenever you want to convert another sampled analog data point, you reset it one more time, and then release it, and then do all the conversions. Still not making sense, I can tell. Where is the point that you guys are not understanding?
Because I just don't understand each block
It's a D flip-flop. Rising edge is going to send D to Q.
Okay.
Okay, and if you are not using,
Rising edge on
yes,
okay.
And if it's not used as a D flip-flop, you can set or reset it. If you set it, you put a 1 to Q. If you reset it, you put a 0 to Q. Okay, no matter what D is. If you're using that as a D flip-flop, you feed a clock to the clock pin at the rising edge. It's going to send, no matter what D is, it's going to send D to Q. If you're setting it, it's directly put a 1 here, no matter what D is.
When you say if you're setting it, do you mean if you're putting 1 or 0 to the set pin, or just if you're putting 1 to the set?
No, you have to put a 1 to the set pin to set it.
Okay. And if you put a 0 to it,
It releases it, it becomes a D flip-flop.
okay.
It sends D to Q.
So the first one, you're setting it, so Q is 1, and then the rest you're writing 0 to the set, so it's actually a D flip-flop, so it's sending 1.
Yes.
Okay, that makes sense.
Now you got a 0 here, right? The next cycle you got a 0 being sent to here.
And then all of the other ones,
You'll got this one being shifted to the right. because all the other ones are not being set or reset because it's being released after the first cycle already. So it's already released. All of them after the reset cycle, all of them are D flip-flops now. So for all the rest of them, okay? So that one will be able to shift it to the right because it's being registered to the queues. And every time one will be shifted here, shifted here, shifted here, shifted here, shifted here, shifted here, shifted here. Okay?
So what happens when one gets written?
It's resetting it. So you're getting a 0 for the queue. That's what's happening here. I connected that pin to the set of the first one and then reset all the following ones.
Yeah. So that first increment when one gets written to the set, the other one.
Yes, that's why you are getting 0 for the rest. You're making sure you're getting 0 for the rest because you want this one. Whenever I put a 1 here, one of this one to reset all of them. Mm-hmm.
So that first one, when you write one at the start, it's like initializing everything.
Mm-hmm.
Basically.
Yep.
It's telling them, it's setting the first one to 0 and then it's using the reset pin to set the other 4 to 0. Or it's writing the first one to 1
Mm-hmm.
and then using the reset pin to set the other one to 0.
That's right.
And then from then on, it's writing 0 to
For,
stops the other one, the other 4 from changing, and they're just getting shifted over. And then
they are changing because after the first cycle here, right? Because it's not, they're not being reset because I put a 0 right after that.
Yeah.
So only the first cycle I put a 1 here to reset all the following ones, but after that I release them so they become D flip-flops. They are able to register D to Q, right? That allows the one, for example, the second cycle, that allows this one to be registered here. That's why you are getting a 1 here.
So they're getting
Is they are being shifted.
okay. And then you're writing, or you're putting the 0 to the set, so then that first one is adding a 0 to the start.
It's not adding because I put a 0 to here, so all the D flip-flops are able to function as a D flip-flop, right? They're not being set or reset. They're going to follow D.
Yeah,
okay, so D was 0 at the very beginning, and they're always 0. So whenever clock, you're getting new zeros. The new zeros, so the 0 is providing a 0 to all of the stages, right? And but the 1 is there's only one 1 here, and it's being replaced by 0 every cycle. Okay, so only one 1 here will be shifted to the right until here. Mm-hmm. So what is this one doing eventually? Is this one will be shifted out? If not, what is this one doing or going to do? So where is that one? Can you show me in this circuit? Yeah, it's going to be here, right? Mm-hmm. So what is that one doing? So whenever it was 0, right, it changes from 0 to 1. So you're flipping that 0 eventually to 1, right? Will be set, right? Will be set. So will be set. You are getting a 1 here. Mm-hmm. Mm-hmm. The rising edge. Mm-hmm. It's gonna do what? What is that D? Yes. Mm-hmm. All makes sense, right? So now you know why do we need the last one. We do need the last one. And we do need the last one here for the sequencer as well to hold that one. Okay, to set the last D flip-flop for the code register in order to trigger the fourth one. Any other questions about this circuit? Okay. I don't have enough time to go through the unwell, so tomorrow the lab is going to be unwell, so we'll do it in 2771. For electrical VLSI, I'm going to give a quick lecture at the very beginning, maybe for like 10-15 minutes, and then you can do your lab. So make sure you'll be there on time. Okay. Call it today. And also the homework assignments I saw you, some of you guys posted to the website. I was not expecting that. I was expecting a paper turn in, but you post it on the website. You don't have to. I think it's just adding a lot of workload. You have to scan it and just put on the paper and turn it in on the due date. Just at the very beginning of the lecture. Just to have it. If you have it, turn it in. If not, it's fine. If you already posted to the website, it's okay, since I didn't tell you. Either way, okay. It's also easier for me to grade, and I can put my comments on it easily, give you feedback on it.